So in this section, we're going to be looking at the connections between a function, its derivative, and its second derivative. We're looking at the graphing connections and other things. This is general all-purpose information we want to look at to how I can use different things to answer certain questions. So connecting graph features. So if I look at this right here, I'll see that I have a function graph, I have its derivative, and I have a graph of its second derivative. And so when you look closely at these things, you can see the features of the original function and how I can use these graphs to help describe what's going on over here. F has horizontal tangent lines at A and B. So the horizontal tangent lines in a graph manifest as the zeros in the first derivative. Okay. F has a point of inflection at C. So then in the first derivative, that point of inflection becomes a relative max in this example, or a relative minimum. And that point of inflection in the second derivative is a zero. So the relative max and min value here, see there's a horizontal tangent here. So that means that in the next derivative down, that's the zero over here. And that's what I said right here. So F prime has a horizontal tangent at C, and the second derivative at C is zero. So these are how these things are connected. You can see over here that on the left of A, F prime is negative. So over here, we can see that the function is decreasing. Then I'm above the x-axis, so F prime is positive. So between A and B, F of x is increasing. And then it goes back down again, and so forth. And so we can use these kind of things to help us see this. In the second derivative, this right here is positive. And so if the second derivative is positive, that implies that the original function is concave up. And then when F prime is negative, we are concave down. Okay. This here is positive. That means the first derivative was increasing. This over here is negative, so it means the first derivative here is decreasing. So the same rules applies, and just depends on the order in which the derivative is written. Justifications for graph features. You want to know this because you're going to use, you may have this picture and you want to talk about this function, or you have this picture, you want to talk about this one, or vice versa. So we need to learn how to do our justifications. So here is a chart for you guys. F of x is increasing, means the first derivative is greater than zero. Decreasing, the first derivative is less than zero. If I have a relative max on the original function, if I have a relative max at C, then the first derivative will be zero or undefined and changes from positive to negative. And then over here, F prime of C will be zero and F double prime of C is less than zero. Do not have that. This is the second derivative test. Here it is for the minimum, again, all the way through in the second derivative test. Concavity. F of x is concave up, means the derivative is increasing, and it means the second derivative is positive. And concave down, just in the other direction. Point of inflection. F has a point of inflection, then I can describe. So when I say by justification, it means if I have a first derivative, I'm just looking for the relative max and min. If I have the second derivative, then I would go this direction. I guess I should have made that clear. Okay, so these are all the justifications and ways I can show this thing over here. I can do it with this, or I can do it with that kind of a thing. Okay, especially the concavity. A lot of times people get locked into the fact that it has to be the second derivative being positive or negative, but I can use the first derivative as increasing or decreasing to explain the same thing. And F prime for a point of inflection, a lot of people automatically go to the second derivative, which is fine, but you can also show it. The point of inflection is going to manifest as a relative max and min in the first derivative. So that's why we're looking at this, so we know all the different ways to do it. The point of inflection is the greatest or lowest rate of change. It is the highest slope or lowest slope, depending on your situation. And f prime of x has a max or min there, which is what we set up in here. What do derivatives reveal? The first derivative, f prime of a function, gives the slope of the function at any x value. F prime greater than 0 means the slopes of f are positive, and f is increasing. And likewise, if f prime is less than 0, then the slopes of f are negative, and f is decreasing. So basically what this is all about is just learning the relationships between the different functions and how I can use them to do different things and answer different questions. Here is a second derivative. What does that tell me again? Just reiterating the same things. The second derivative gives the rate of change of the slopes and concavity. If f double prime is positive, the slopes of f are increasing. The slopes of f are increasing, and f is concave up. And if it's negative, then the slopes of f are decreasing. This means like f prime, and f is concave down. So here are some examples. Instead of rewriting on this one, I just wanted to show them and I want to redraw the pictures. So here's an example. The graph of f prime is shown. This is the graph of the derivative. And it is known that f of x equals 0. I think that might be a typo. Which of the following could be the graph of f? I think this should have been f of 0 is 0. But anyway. So look at this picture. Which one of these could it be? So let's analyze this graph over here. This is the derivative. We're talking about what is f of x. Okay, which one of these could be the function that it came from? So I look at this and I see, okay, what are the key points of interest here? Well, I see that I have zeros at 3 locations. Okay, 0, actually 4. 0, 2, 3, and 4. Okay, so I'm looking to see that these are zeros, so that means I had horizontal tangents in the function there. Okay, so I look at this graph over here. Do I have any of those situations? It looks like I have it here and here, maybe here and here. Then we need 2 and 3. So here and here, and this is 4, right? 1, 2, no, this is 3 and 4. Yeah, but there's one extra one here. See, so that's the problem. I think B is out because of that. I don't have it. This is a horizontal tangent right here. I don't have a 0 at 1. So this one is out. This one over here is also out because at 1/2 I had a horizontal tangent. There's no 0 at 1/2 over here. So that one is out. Okay. It could be this one, and it could be this one. All right. What else do I know? Well, I know that the derivative is positive between 0 and 2, which means that between 0 and 2, the function should be increasing. Yes, this function is increasing, and this function is increasing, so we're good there. It should be decreasing between 2 and 3. Yeah. Yeah. And then increasing from 3 to 4. Yep. And yes. Okay. What else do I know? And we just keep on going through all the different things. What does this tell me? What are the things I know about this? Okay. Here, we can look at the second derivative concept of concavity, correct? But I don't have the second derivative, but I do have the derivative, so I can talk about the slopes of the function. The slopes of the function are increasing or decreasing. So if the second derivative, right, is positive, then the original function will be concave up, but the slopes of the function should be increasing. Okay, so here, these are increasing, and here they are decreasing. Okay, and here we have the slopes are increasing, and then they are decreasing. So we need to look for something that does all that. Okay, and so we're looking over here, and so that means what? From here to here, since these are increasing, it should be concave. Should be concave up between 0 and 1, and then concave down between 1 and 2. Well, this one is concave down all the way from 0 to 2. So this one is now out. Here I have a concave up, Then I have a concave down. Okay. Then I still have a concave down. And then I have a concave up, and it's this one right here. So the correct answer for this one is C. Okay. Here's another example with some tables. The function is known. Okay, the function f of x, it is known that f prime of x is positive and f double prime is negative for all x's. Which of the following could be a table of values for this function? So what does this mean in context to the function? Well, if I tell you that f prime of x is greater than 0, that means the values of the function must be increasing. And it's for all values of x, so that means it's always increasing. So are there any graphs, any tables where the values of the functions, as we go down the line, and you'll notice that all the x's are increasing here? Okay, same way. Is there any one of these tables in here where f is not increasing? That means each y value has to be a bigger number than the one before. And so this one is still okay. This one right here, we went from 11 back down to 9. This one is already out. These are negative numbers increasing, yes. These are numbers increasing, yes. So B is out because of the fact that it's not always increasing. Okay? And so we keep doing this thing, and we keep looking around and seeing what information we have. This one over here means that the rates of change, right? If this is less than 0, the slopes of f, the slopes of the function are decreasing, which means the rates of change have to be decreasing. So you can take a look at this and see all the rates of change in between. This is where you just kind of do little slopes here and see if the slopes are decreasing as you move along. So I'm going to go ahead and reveal some of the thinking behind this problem so you can see it, and we can discuss the answers that I have written down. And you can see right here, this one is out because it's not increasing. F prime of x greater than 0 means it's always increasing. F double prime less than 0 means the slopes are decreasing and we are concave down. Find the function that is increasing at a decreasing rate. Okay? And so like I said, we can go through here and find the little rates of change for these problems right here and here and so forth. And you can go through and figure out that which one it would be. We need to be at a decreasing rate. That means the slopes have to get smaller as I go up. So the gap here is 10. Then this gap is 7, then 4, then 1. This gap, I'm doing the slopes, y2 minus y1, x2 minus x1, which these are always the same for all of them. So I'm just looking at the y changes. This is plus 2. And then this one right here is, I'm sorry, this right here is minus 2. Then this one right here is minus, no, it's plus. Plus 2, plus 5, then we have plus 8. So these are increasing. Plus 10. This one right here is minus 2. Well, this is already out. This right here is plus 2, then plus 3, then plus 6. So these are increasing also. So this is the only one that is the slopes of these points are decreasing. Here's a graph. The graph of the derivative is shown. This is the derivative, f prime. On what interval or intervals is the function increasing? So these are questions that you could be asked. So the function is increasing, okay, when the derivative is positive. So we can see in here that we have it's positive here and it'd be positive over here. It just depends on what intervals we're looking at. So let's take a look at this one. Again, how to think about it. When f prime of x is greater than 0, the function is increasing. So when is it greater than 0? It is greater than 0 from here to here, which is negative 3 to positive 2, and from 5 and on, because f prime is greater than 0 there. So when we talk about increasing or decreasing, remember we use closed intervals. All right, let's take a look at the next one. So we look at this one right here. The graph of f prime, the graph of f prime is shown. So again, we're looking at the derivative. At what x value or values does f have a point of inflection? So if you remember, in a derivative sense, the point of inflection would be any relative maxes or mins. Okay? So that would be in two locations right here. So let's take it and do a reveal here. What should I be thinking about? F has a point of inflection when F prime changes signs, which means the slopes of F prime must change. Okay, so I must go, here is positive, here is negative, correct? The slopes of F prime. So these slopes are positive, these slopes are negative, so it happens at the relative extremis on the derivative. F has a point of inflection at 1 and at 3 because F prime, F double prime, the slopes of F prime change signs. So that's a way you can address it based off of what you see. When you write a justification, you have to use what you were given to do it or show how you got it. Okay? So here's another example right here. The graph of the second derivative is shown. On what intervals is the function f concave down? So you need to remember that for the second derivative. Okay? If the second derivative is negative, then we are concave down. And so we can see that we have two spots where that is going to occur. So again, when you look at these problems, always talk about what it is I know and how I can use what was given to me to figure this out. Okay, f is concave down when it's negative. F is concave down on these intervals from -2 to -1, and from 1 to 2 because the second derivative is negative there. So here's another one. Here's a graph of a function. On what intervals is f prime increasing? So the part you need to learn from this is, what does it mean for f prime to be increasing? How is that? How do I use that from this picture? What is it? How is it going to manifest? And that's why I did this one for you guys, so you can kind of see the connections and learn the connections between things. These are questions that were happening on AP all the time. Okay, so let's go ahead and look at this. How to think about it. F prime is increasing when the second derivative is positive. Okay, which means what? When the second derivative is positive, it means f of x is concave up. So I look over here, where is f of x concave up? From 2 and above, correct? From 2 and above. That's where it's concave up. This is concave down. So f prime is increasing on the interval from 2 to infinity because f is concave up, which means the second derivative is positive there. See, that's how you want to look at this. That's how you want to think about these answers. The last one right here is, I give you this picture. There are 3 graphs drawn in here. You have A, B is the parabola, and C is this one right here. Okay? So the graph of a function, f, its derivative and its second derivative are shown. Which one is which? So I have a function, I have its derivative, and I have its second derivative drawn right here. You have to determine which one of these is those. Okay? So what you do is you look at the characteristics. Okay? You see what's going on. Look it around. Look for things where I have peaks and valleys become zeros. So for example, in this graph right here, I have horizontal tangents here and a horizontal tangent here. So the derivative of this function c is going to have values that are 0 there. So I have a graph that has zeros at those 2 locations. And sure enough, I do. Okay? And so we can just go through this entire argument for all of these. And let me go ahead and show you the argument here. And tips and things to think about. If a function has maxes and mins, its derivative must be 0 or undefined at that value. So look for that kind of stuff like I just told you. If a function is increasing, its derivative must be positive about the x-axis. If decreasing, its derivative is going to be negative. I'm sorry, this is above, not about. Above the x-axis, and this one is below the x-axis. So we look for those 2. So we already did that one here. The B curve has a minimum between 1 and 2 because there is a horizontal tangent. So the B, yeah. So I don't know why I wrote that one. A curve is 0 at its x value. So look at B. B has a horizontal tangent right here, and A has a 0 there. That's what it was talking about. So because of that, A is the derivative of B. C has 2 horizontal tangents. The B curve has zeros at those locations. We did that one already. So that tells me that B is the derivative of C. Notice that the A curve is always increasing, meaning its derivative must be above the x-axis of its domain. And I have no graphs that behave that way. Okay? So that means what? A has to be the second derivative. I have no derivative for A sitting up here, so A has to be the lowest derivative, which is the second derivative. Then B is that, and C is that. Okay? A had to be the derivative of B, and B had to be the derivative of C. Okay? And so there's your way that you determine which one is which. Okay? So learn these connections between these. It's going to help you tremendously on tests. And that ends this video.